Hi everyone. So we had talked in the last video about the easy conversion factors going from meters to kilometers to gigameters to terameters with metric, and that's great, but we've still got too many zeros to deal with. And we're going to now get rid of the zeros in the second step of using scientific notation for exponents. And don't fret, this is easy stuff. So I've kept it pretty easy so far, and let's keep going. Now, as I said, we hate all these zeros. They just lend us toward making mistakes, putting another zero here, forgetting a zero there. Look at this. If I have 160 quintillion meters, I could make this so much easier. I could count all of these zeros. I've actually got 19 consecutive zeros from the decimal point. Count them up. 3, 6, 9, 12, 15, 18, 19 zeros before I get to my numbers, which happen to be 16. So look what I can say. 16 times 10 to the 19th. Got 19 zeros. Those all represent a power of 10. 16 times 10 to the 19th meters. So much more precise for and easy, even space-wise, to put this into data charts. So that's why we're really going to be concentrating on scientific notation. All you're doing is finding the decimal point, counting the number of consecutive zeros to the left, and putting that number of consecutive zeros into the exponent, a power of 10. The numbers that are in front of those zeros are your numbers that go as your factor there. This is a factor, 16 times 10 to the negative 19th. Look at, we can even make it even better. We could say 16 times 10 to the 10 to the 19th, or we could make this number between 1 and 10, which is a really scientific way to look at numbers, between 1 and 10. And we could say, look, 16 times 10 to the 19th, move this decimal point one more place over to the left, and it could be 1.6 times 10 to the 20th. 19 plus 1. We moved it over one more power of 10. So when we look at scientific numbers, we like to have the factor between 1 and 10. This is a great way to do it. This is correct. 16 times 10 to the negative. I'm getting into negatives because I'm a biology person. 16 times 10 to the 19th meters is absolutely correct. And 1.6 times 10 to the 20th meters is absolutely correct. All right? Now, kilometers, just still too small. And the English were not really ready for metric back in the 1700s. So they went for a bigger unit of measurement called an astronomical unit. It's basically the distance from the Earth to the Sun. This was very important for hundreds of years because we thought that there wasn't much out there besides the Earth, Mercury, Venus, the Moon, the Sun, a few planets that we could see, not much else. So scientists drew out another unit of measurement called an astronomical unit, which is the distance between the Earth and the Sun. You don't need to really concentrate on that. It's antiquated. We know so much more now. We really don't use AUs, but I wanted you to know it because I really love history, and the history in astronomy is so long and so important. So I thought I'd let you know. As we learned more about the universe, we had to come up with a better unit, a better, bigger unit than astronomical units. So we came up with light years. And it's a great unit because light is the fastest known way to cover a distance. There's nothing faster than light. In fact, light moves at 300,000 kilometers per second. And The circumference of the Earth at the equator is 40,000 kilometers, meaning that light goes around the equator 7.5 times per second. It's the fastest measure that we have. So to cover these huge distances, we use the measure of light years. It is a distance measure, and it is a way for us to cut down the enormous numbers and the enormous zeros. Before we started working with scientific notation, we used to say, oh, it's 93 million miles to the sun. Well, now we can say that the sun is a fraction of a light year away. In fact, light from the sun takes 8 minutes to reach Earth. It seems a really long time, but it's not. And the light year is the distance that light can travel over an entire year. Now think about it. If it takes 8 minutes for light to leave the sun and get to Earth, you can imagine how much distance a light year covers in the distance that light can travel in 1 year. This is a distance measurement. It is not a time measurement. In fact, if you say to somebody, oh, that would take me light years to get done, you have the wrong definition for light years because you are expressing time. This is a distance that we are expressing with light years. But it is hard to understand because it has years in the title of the unit. So this is a distance measurement, not a time measurement. Something to really keep your head around. This area that you see here is approximately 17 light years across. So it takes 17 years for light that is way beyond our solar system and out towards some of the much bigger galaxies to move over in this view, 17 light years. Not an easy representation for you, but here's an easier representation. We talked about Proxima Centauri, which is the closest sun to our solar system. We talked about it. Remember, it's the grapefruit that is in San Francisco versus our sun, which is the grapefruit at the Air and Space Museum in DC. Okay, so Alpha Centauri is right here in this drawing. It's not the big star there. It's the little itty bitty star there. And I keep saying Alpha Centauri. Sorry, Proxima Centauri. Proxima actually means nearest in Latin. So it's called that for a reason. And the light from Proxima Centauri takes over 4 years to leave that star and get to Earth. So as you see here, this is about 17 light years across in this view that we have here. Now, how much distance is in a light year, you might ask? Well, we can do the calculation. And the calculation is bringing in another thing. So we've talked about converting metric system, and it's really easy to convert from meters to kilometers to gigameters to terameters. Just move the decimal point around. And we've also talked about counting the zeros and making an exponent so you have a simpler way of expressing distance. Now we're going to go back to working with a few complicated conversion factors, but you can do this. I'm going to show you how to do it. So let's say we know that the speed of light is, look at it, 1,080,000,000 kilometers per hour. That doesn't tell us what the distance is in a light year, because we only know the distance in a light hour. And we really want to know the distance in a light year, but we can calculate it. And we want to calculate it because way too many zeros in here. So let's get rid of the zeros first when we're talking about a light hour, and we can do that. Count the number of consecutive zeros to the left of the decimal point. And that is, look at this, 3, 6, 7. 7 consecutive zeros to the left of the decimal point. So we can make it 10 to the 7th power and include the factor that is in front of all those zeros. Take a look. 108 times 10 to the 7th power kilometers per hour. Much easier to work with. We can make it even easier and put it between 1 and 10 for the factor. So if I have my decimal point here, I could get to 1.08 by sliding that decimal point to the left 2 more places, and then I'd add 2 more places to the exponent. There's my mouse. So I am thinking 1.08 times 10 to the 9th. I thought that would show. Yeah, there it is. Okay, 1.08 times 10, 7 plus 2, because we moved over 2 more places, means that it is 1.08 times 10 to the 9th kilometers per hour. Okay, that's all very fine and good. We made it simpler for kilometers per hour, but that's going to get us to light years and distance in light years, but we're going to get there. So we need 2 conversion factors to do that. And conversion factors are based on the fact that it is a fraction that's equal to 1. So we need 2 conversion factors. We need to go from light hours to light days. That's 1 conversion factor. I'll show you in a second. And then we're going to go from light days to light years. That's another conversion factor that I'm going to show you in a second. The conversion factor is in yellow. Let's take a look at how it equals 1. We could say 24 hours equals 1 day. Both of these things are equal. 24 hours is equal to 1 day. 1 over 1, this equals one thing. 24 hours equals 1 day. So a conversion factor is 2 different measurements that equal 1. All right? 24 hours is the same as 1 day. That's our conversion factor. We can put it in here and we can then cancel out, because I have in here 1.08 times 10 to the 9th, and I'm sorry, every time I do this, it removes my exponent, and I'm sorry about that. I had just saved this, and when I save it, it removes the exponent. It's a problem that I'll try to solve on the PDF. This is supposed to be 10 to the 9th kilometers, okay? 1.08 times 10 to the 9th kilometers per 1 hour. And then I can multiply that effectively by 1, 24 hours over 1 day. Same thing, 1. And I can cancel my hours, and I am left with 1.08 times 24 times 10 to the 9th, I will correct that, over 1 times 1, and I get 25.92 times 10 to the 9th kilometers per day. Okay? And so now I have light days. I got to get to light years. I need 1 more conversion factor. And this still didn't do the exponents. I'm very upset about that. But I think you can work with me on that. There's something with PowerPoint that it's taking out the exponents. So I am at my light days. I've got 25.92, basically 26 times 10 to the 9th kilometers per day. And I've got another conversion factor to get to years. 365 days is 1 year. This is a fraction that is equal to 1. It has 2 different measurements, 2 different units, but 1 over the other is equal to 1. And I can multiply anything times 1. So I can take my basically 26 times 10 to the 9th kilometers per day and multiply it by 365 days per year and cancel out my days and cancel out my days. And I am left with basically 26 times 365 times 10 to the 9th kilometers per year, which equals basically 9,500 times 10 to the 9th kilometers per year. But I don't really like the 9500 because there's too many zeros.